Hey guys, so in this video, all I'm doing is going over the review problem set. I'm just going to go through each problem kind of step by step like I would do in class and just kind of explain things, okay, for anyone who wants a little bit more of an in-depth discussion on what's happening with each of these questions. So feel free to bounce around in the video if you don't want to listen to, a particular problem or whatever. I'll probably do this for things like exams and, maybe particular problem sets that seem to have some tricky things going on. So we'll kind of do these as a as-needed basis, but I figured this would be a good idea. So let's kind of get started here. So with number one, we have the following molecule, right? And we're just circling and naming 7 different functional groups, okay? And so most of these are easy, right? We know we have our alcohols here. If I can spell correctly. No, I spelled that right? Alcohol, cool, okay. And we have things like alkyl groups, right, or alkanes. We have ethers. We have aromatic rings, or arenes, as some of you have been calling them. We have amines. We have ketones. We have alkenes, right? Maybe this is technically actually a cycloalkene, but, whatever. So these last two here, right, we have an amide, or amide, depending on where you live. And one thing you don't want to do, right, is you don't want to call this an amine, right? This is not an amine, this is an amide, okay? The same way you don't want to call a carboxylic acid an alcohol or a ketone, right? This, right, is a different functional group than a ketone would be, right, or an alcohol, right? This is pretty acidic. Alcohols are not as acidic, and certainly ketones, right, are not as acidic, right? There's different functionalities between these different ketone moieties, right, these different ketone groups. So you'll make sure we have that in mind, okay? All right, so for the second problem here, you see I've already done this answer key, I'm just kind of redoing things. Let's look at some of these naming problems, all right? So for number one, or A, we have our parent chain, right, 1, 2, 3, 4, 5, which is cyclopentane. Right, we have fluorine here in the 1 position. We don't need to say 1-fluoro, so we won't. But you can if you want to. So fluorocyclopentane, and that's it. Right, even though this fluorine is on a dash, right, don't forget that with chirality, if groups on either side are the same, right, it's in a ring like this, there's no chirality, okay? So calling this RS would be wrong, right? It doesn't have chirality, right? Important to keep in mind. So for the second problem here, we have a hexane parent chain, right? 1, 2, 3, 4, 5, 6. So we know we have hexane. On that 3 position, we have an iodo, and we have methyl. Right, 3-iodo, 3-methylhexane. But we also have a chiral center now, right? We have 4 different groups coming off of that central carbon, a methyl, an ethyl, propyl, and iodo. Okay, so we have to make sure we're doing chirality naming, right? So in terms of priority, right, pretty easy. We know iodo is first, and then we're looking at our 3 different carbons here, right? The more carbon chains on it, the longer or the higher priority it is. So we know iodo is 1, propyl group is 2, ethyl group is 3, and our methyl group already in our back position is 4, right? So we're going clockwise, right, which we know is R. So we have R, or 3R if you want, 3-iodo, 3-methylhexane. For C here, kind of going backwards, we're doing a parent chain first. We have bromo in the 2 position, chloro in the 3 position, and now the question is, okay, is it a wedge or a dash? Is it R? I mean, yeah, there are, but right, we have to make sure they're connected appropriately to BR. So let's, for now, put them on wedges and see if it makes sense for what we have, right? So if we have bromine on a wedge, that means we have a hydrogen back here on a dash. And so we can do, right, bromine is 1, this carbon here is 2, right, it's connected to a chlorine, and then this methyl group over here is 3, of course hydrogen is 4, so we know we're going clockwise, so we know it's R. And down below for chlorine, we'll do this in purple to not get our numbers confused, right, chlorine is 1, we have a hydrogen on a dash that we know is 4. This is 2, this is 3, and so we're going again, and I'll just put this hydrogen here, we're going clockwise, right? So don't be confused, right, that if you start drawing it this way, it's not counterclockwise, right? We're going all the way around still, right? This is still in the clockwise direction, right? It's not this way. So this is R, okay? With this bromine and this chlorine on the dashed, or on the wedge positions, right? Kind of get rid of some of this extra junk here. Okay, so let's look at these two bottom naming problems now. So we have a alkene here, so we have to figure out E or Z eventually, right? But for now, let's go ahead and number this thing. 1, 2, 3, 4, 5. And we're looking at this, right, and we can see the majority of our numbering, right, is on the lower side. We have 2-chloro, 4-methyl, 2-ene, right? That alkene is in that 2 position. Right, if we went from right to left instead, we'd have a higher overall numbering of 2-methyl, 3-ene, 4-chloro. Right, but here we have 2, 4, 2. Right, so it's overall lower numbering. Okay, and so if we're putting this together, we have 2-chloro, 4-methyl, and then right, pentane, pent as our parent here, so pent 2-ene, and then right, do we have E or Z going on here? So if we're looking at this alkene, we know chloro, right, is our highest priority substituent on this side, methyl is low priority, and on this other side here, of course, hydrogen is low priority, and this isopropyl group here is high priority, right, when we're looking kind of across this double bond. So the groups are on the same side, right, so we have Z, right? Again, that phonetic I use is zame, zide, and E is opposite, right? High priority groups are on the same side. For the final one here, once again, let's go ahead and name this. So we're starting from, right, the alkene, right? We see that that's going to be in our 1 position instead of the bromine on the 2 position. So we have 4-bromo, 1-ene, pent once again, and now we have a situation where once more we need to figure out RS, right? Because this is a chiral carbon. So we have 1 second priority, 3rd priority, and our hydrogen in the back, of course, is 4. So we have counterclockwise, right? We can start drawing an S here from that. So we know we have S as well. So stringing this all together, we have S, 4-bromo, pentene. We don't need to say 1-ene. We can if we want to. It's totally fine to do that, but this is fine. And also notice, right, this alkene is not E or Z, it's not cis or trans, right, because we have 2 hydrogens off the end here. Right, so there's no lower high priority, so it doesn't matter, right? They're both. Or they're neither E or Z, right? It's not a stereo isomer at the end there. All right, for number 3 here, let's go ahead and look at these problems. So for number 3, when these go for any of these reactions, we need to be considering what are the conditions here, okay? What reaction could be taking place? You know, I've kind of segmented this pretty rigidly to make sure we're doing SN2 or SN1 or E2 or E1 reactions, okay? With the caveat that, right, we can have E1 and SN1 occurring at the same time. So that's kind of the only thing we really need to be aware of. So we're looking for, again, the major product. So when we're looking at A, right, we know we have a strong base. We have polar protic solvent, and we have heat. So these are all, right, E2 conditions, particularly, right, that strong base, okay? So these are really important to keep in mind, okay? If you're having some trouble figuring these out, definitely look back at your chapter 6 and 7 notes, okay? And so we know for E2 reactions we want to follow, as long as there's nothing tricky going on, Zaitsev's rule, where we're forming, right, the more substituted alkene. So you might think initially, okay, right, there's more carbons over here, let's form our alkene there. But the issue with that, and I'll show this in red, so if we try to form this alkene, we can't do that because this carbon, right, has 5 bonds. Right? This carbon here has no hydrogens on it. Right? It already has 4 bonds, right? It has a methyl group, a methyl group, a methyl group, and is attached to this carbon here. So it can't make an alkene in that position, right? And because this is E2, there's no shifting going on, it's all concerted, right? This is a concerted mechanism. So the only thing that can occur is the base taking an adjacent hydrogen here from the only available spot to form our alkene here. Okay, it's the only available hydrogen for that strong base to take. Okay, hopefully that makes sense. For B, same things, right? Slightly different things going on here, but we have a strong base, and this is not particularly bulky, okay? But it is, right, a strong base. We have polar protic solvent and heat, again, E2 conditions. And now we have 2 different options here, right? We have 2 carbons with hydrogens on them. Right? We have to keep in mind the chirality, okay? And what's important here, right, is for E2 reactions, the hydrogen and leaving group must be anti-periplanar. They must be, right, 180 degrees, right, that dihedral angle apart. As we can see here, the only hydrogen and leaving group that are different like that are these two, right? The iodine and the wedge coming towards you, and the hydrogen going away from you, right? So this allows the strong base here to take that hydrogen and have these electrons kind of fall like a domino and remove the iodine. This hydrogen here on the left and this iodine are on the same face, right? They're both coming towards you, they're not opposite. So that reaction is much slower, okay? That would be the minor product of anything. So our product in this case is just this alkene here. Where now, right, this methyl group is no longer in a wedge, right? It's flat, it's in the plane. This is a trigonal planar carbon, right? sp2 hybridized, trigonal planar geometry. So drawing on as a wedge would technically be wrong, right? We have to sort of keep in mind that these carbons are no longer tetrahedral, they are sp2 hybridized and trigonal planar, right? They're flat. Number 3, we're seeing similar conditions, but now we have a weak base, okay? And no heat, right? So elimination is not dominating, right? It's not the only thing happening. Meaning, right, we have SN1 conditions here as well as E1 conditions. So we can't really say if one is taking place over the other, we're gonna get a mixture, okay? And in either case here, we have, right, for E1 and SN1, the leaving group leaves first, right, so we have our carbocation intermediate, and then we have 2 different things take place, and I'm going to show these in different colors, right? We can have an SN1 happen, where alcohol comes in as a nucleophile, or we can have an elimination reaction occur, where our base comes in. Right now it can also be, right, it's a weak base, but also a weak nucleophile, so that it will come in as a weak base and form an alkene, right, just like this. And then for the SN1 reaction, right, we end up forming this ether here, right? That hydrogen is there in the beginning, right? That hydrogen hasn't just magically left, but it needs to get removed at the end to be neutral, okay? So these are the 2 different reactions taking place here. All right, for the final one here, we have, once again, this strong base, quote unquote, but it can also be, right, a strong nucleophile. And we have, right, polar aprotic We only see polar aprotic solvents like DMF and DMSO when we're doing SN2 reactions, right? Where we have this nucleophile come in and attack the backside of this carbon leaving group bond, and so we're forming this ether as our final product. All right, so let's look at these next two reactions, or three mechanisms rather. There's one on the next page. Okay, so we're given the product, so we know what's taking place, right? We know the final thing that's here. So we'd figure out, okay, how do we do air pushing mechanisms to get there? And so we need to consider what's available to us, right? We have, right, for A here, we know we have polar protic solvent, right? We have a, decent nucleophile, right, but still kind of weak. And then we see where we have a substitution taking place, right? There's not an alkene or anything, it's just a substitution, right? One thing has taken the place of another. And so, right, this has to be SN1, right? Particularly because of that polar protic solvent. So in the first step here, we know we have our leaving group leaving, right? That Br has left. And now, right, we think, okay, we have our electrophilic carbon. Can our nucleophile just come in and attack here? No, right, because that's not the product. The chlorine is not here. So we need to think, okay, what can we do? And something we learned back in chapter 6 is we can do these hydride shifts, right, to get to a more stable carbocation. Right? So now this carbon has technically two hydrogens. But this carbocation, right, is now on the tertiary carbon, right? This is more stable than a secondary carbocation, okay? So now we can do our final nucleophilic addition, where our nucleophile will attack our electrophile, right? It's going to come in and make this new carbon, or make this new covalent bond between the chlorine and the carbon to get us the product we see up above. For letter B here, we have polar aprotic. So we know, right, SN2, right? It has to be. And we can see that too, because we're not forming an alkene, we're having a substitution occur. Where something, right, this amine here, has replaced our chlorine. And so it's important to recognize that, okay? When we're doing these mechanisms. We don't want to just, kind of make guesses. We want to at least, right, guesstimate. We want to at least get pieces of what's going on and try to conform that to what the question's asking, right? We want to do a mechanism, so let's do an SN2 mechanism. Right, so it would be wrong to have chlorine leave first, right, because also, right, primary carbons are not, right, they're not good carbocations, right? So we know, right, we're just having a substitution take place. And so what does that look like? Right, we have this amine, which is a good nucleophile, right? Things don't have to be negatively charged to be a nucleophile. This amine is coming in and attacking this chlorine, or that carbon attached to the chlorine, and it leaves. So we get the following intermediate, right? This positively charged nitrogen here, right? Do we see that? With Cl- as our leaving group. Now the only thing we need to do, right, and we've seen these intermediates before when we have a positive charge left over, right? We've seen that with alcohols during SN1 reactions. We need to just neutralize the final product to get to something more stable, right? So we just have this chlorine deprotonate that ammonium ion here to get to our final products, right? Where we have HCl and this neutral tertiary amine here, okay? So this is technically, right, an intramolecular SN2. And for our final reaction here, we once again, right, have these E2 conditions, right? We have a strong base. It's bulky in this case, but it's still, right, our strong base polar protic solvent and heat. We have an E2 reaction. And with E2 reactions, we know we need to have the hydrogen and leaving group antiperiplanar, right? Like we discussed in the E2 reactions a few questions ago. Because if we did this reaction as is, right? Let's say we took this bulky base and said, okay, like let's attack this, right? We have our hydrogen, we're removing bromine, but that wouldn't get us this product, right? Because, right, we see our methyl groups here, they're on the same side. And so our actual product, if we did that, would be the wrong stereoisomer. Right, we see that? This is Z, right, highest priority groups on the same side, and this is E. So this is the wrong way to generate the alkene. What we have to do is a bond rotation to get the hydrogen and bromine on the right side. So let's rotate the bond here to have that happen. So we'll keep the bromine on the same side, right? Notice we have our methyl group here pointing up, we have it up here, so let's keep that the same, but let's rotate the other side, right? Because we want that hydrogen to be on a wedge. Right, so if we're bringing this hydrogen from the back forward, this methyl group is going forward down. Meaning this phenyl group is taking the place of the hydrogen in the back here. Okay, and if we did RNS configuration for each of these carbons, they'd still be the same, right? So that means we know we didn't just switch groups and make a different molecule. We know that we rotated this bond fully. And so now we can do this elimination, where we have our tert-butoxide, and we can come in, right, and take that hydrogen, which is now antiperiplanar, to the bromine, forming us, or granting us our alkene, okay? And if we wanted further proof of this, how do we know this hydrogen and bromine are really antiperiplanar, right? We know this is kind of a trend where we're seeing something on a wedge and then on a dash. We can use Neuen projections, right? If we were to look at the Neuen projection, and I'm going to erase some of this clutter here, if we were to do a Neuen projection of this molecule and look down, right, that carbon-carbon bond here, right, that hydrogen, right, coming towards us, we're rotating this molecule towards us, that hydrogen is now on the right, that phenyl group is on the left here, methyl group pointing down in the plane, and on this back carbon here, which is behind where this Neuen projection is, right, that bromine, right, is out to the left, right, it's on the same side as the phenyl group, we have a hydrogen over here, and then another methyl group up top. And we can see, right, in that reaction we did, and I'll redraw the arrows, that hydrogen, this one here, is antiperiplanar to the bromine, right? They are 100 degrees apart, right? They're antiperiplanar. All right, I hope that makes sense. So now let's go ahead and look at some more general reactions here. So these are all these chapter 8 reactions, right? And we're kind of seeing these come up time and time again in class. So let's look at a few of them. Right, so for this first one here, we have this halogenation reaction, where essentially, right, we're adding that chlorine across a double bond, right, forming an intermediate first, that chloronium intermediate, and that other equivalent of chlorine comes in and breaks open that bond to get us our final product. For the second question here, we have the dihydroxylation occurring, meaning where we're adding two OHs across the alkene. And they're adding on the same face, right? We have this syn addition happening. So we actually have a mixture of an OH on a wedge. Right, this is not a chiral carbon, but it's fine to show that OH is like this. and then we have the dashed. So we can say plus enantiomer, or right, we can draw in the actual enantiomer here. Okay. So for number 2, right, the reaction taking place here, right, is we're having the substitution occurring, this addition occurring with this alkoxide here. Right, we're seeing these conditions here where we have this oxymercuration taking place. And so what we have to consider, right, is if this was just an H2, or H2O, and not this ethanol, our product would be this, right, this Markovnikov addition of alcohol. But because, right, it's an alkoxide, that whole portion here, right, this whole thing is adding to that alkene. Drew that terribly. Right, O, and then right, that alpha group there. So the whole thing is adding Markovnikov, right, to the more substituted carbon across that alkene. All right, so for this next question here, we have this hydroboration oxidation taking place. Where across the alkene, we are adding an OH anti-Markovnikov. Right, we're adding that OH to the less substituted carbon on the alkene. So across that alkene, we're getting an OH added right there. And on the other side, we have a hydrogen. And they are actually adding on the same side, so we can draw it like this. But, right, these are both chiral carbons, so we don't need to draw in plus an enantiomer, because there is none. That's true for most of these molecules, right? I've kind of cleverly made most of them achiral, aside from this one here. But yes, this is the result, right? This anti-Markovnikov addition of alcohol, right, to the less substituted alkene. And finally, we have this ozonolysis reaction taking place. Ozone lysis, right? O3 is ozone. Lysis means we're breaking a bond here, right? This alkene is getting split in half, but they're tethered together, right? There's this tether in this ring connecting everything to the same face, or to the to each other rather. And so what happens is alkene gets split open, right? And so we have 1, 2, 3, 4, 5, 6 carbons. So let's make sure we're keeping that in place here, right? So we have 1, 2, 3, 4, 5, 6. Right on the 1 position, right, we have that methyl group coming off. We have a ketone here, right? So essentially, wherever there was once an sp2 carbon, keep it sp2 and make it a carbonyl. And for 6, right, we have a hydrogen coming off the end here, and now we have, right, that carbonyl. So essentially, right, we're just splitting that ring open, okay, like this. All right, so for the final reaction here, or question rather, we have this sort of stepwise synthesis problem, where the conditions of everything kind of depend on each other. Right, we need to know what the products are before we move forward, or reagents. So for A here, we have this reaction taking place where we're doing this radical bromination. Meaning, right, we're starting from an alkane and making a alkyl halide. And so when we're doing this radical reaction, right, typically seen with Br2 and light, right, we're generating this bromine radical. There's a radical generating on the alkane as well. And the alkane, or the radical, forms like the carbocation, right, on the more substituted carbon. Right, and this is the most substituted carbon here, so that's where the radical forms. And so we get this, right, homolytic bond formation, or homobond formation, there's no cleavage here, to form, right, this as our intermediate, that bromine on the tertiary carbon. And so for B, we're going to say we have A here, we have an alkene, right? This is pretty clear we're doing an elimination, and we can do E2 or E1. So let's just do E2, right? Let's just do some simple alkoxide, right, a strong base, polar protic solvent, and heat, right? Very easy for that. Bromine eliminates from an adjacent hydrogen, and we're forming our alkene. So next up, we're doing this halohydrin formation. We know it's that, right? It's not just Br2 by itself with an inert solvent, but it's Br2 with H2O, right? H2O can take place in the reaction. And so what does that mean? So when we have Br2, right, or Cl2, the intermediate we're forming is the following, right, where we have our methyl group here. Our intermediate is this bromonium ion intermediate. And normally, right, we have Br minus, but the solvent is H2O. There's just so much H2O that the Br minus doesn't actually react. The H2O reacts. And where does it react, right? That's the question. And so it reacts at the more substituted carbon. And the reason for that, in case you've forgotten, is in these cyclic intermediates here, like this bromonium ion intermediate and epoxides, which we'll see in a minute, there's a more partial positive charge on the carbon that is more substituted. Right, this bromonium ion intermediate is pretty strained. So even though we've drawn it like this, in sort of reality, quote unquote, it really looks like this, where, because that bromo intermediate, right, is so big, it doesn't really want to make full bonds here if it can help it. So there's really this large partial positive charge here as that bond is kind of further apart, right? This is the most strained bond here. So the H2O is happy to come in and is more attracted to that partial positive position, right? Because the more substituted carbon can have a bigger, right, it's more stable with a positive charge. So this carbon is happy to take the brunt of the strain that's happening, right? It's the most accessible carbon right now and most attractive for the H2O. So our product here looks like this, where we have OH, right, and there's a final deprotonation step we're not doing, and bromine on the other side. Notice I've kept the chirality here, right? In truth, we're getting a mixture, right, of enantiomers, but notice our epoxide product further out, and I'll talk about that in a second. We have to be consistent here with what we're doing. All right, so we have our halohydrin product, right, an alcohol and a halogen. And so the step here in the middle, right, is just this SN2 reaction. Where we're using a base, we can use NaOH. I like using a bulky base to really show that we're grabbing that hydrogen from the oxygen. And we can use polar aprotic conditions like DMF or DMSO. And this OH, right, is getting deprotonated to be the O-. And I'll show this up top here. Right? And then it's attacking, right, the backside of this bromine carbon bond to form an epoxide, right? Notice the stereochemistry of the oxygen isn't going to change, right? But its connection to the bromine has changed, right? So there is also, right, a hydrogen here on a dash, and now here it's on a wedge, right? That oxygen has come in from the back and pushed up that hydrogen, right? Because it wants to make that bond on the backside of the carbon bromine bond, so it comes in from the back. So that's why we're getting this formation here, right, of this dash bond from the oxygen to the carbon. Okay, so the next step is similar to what we see in from B to C. We're getting this acid bromide reacting with our epoxide, making it charged. We're getting a positively charged epoxide intermediate. So this oxygen will attack that hydrogen on HBr, and we form this intermediate here. Right, and just like the bromonium ion intermediate, it's pretty strained. So once again, we have a situation where we have more of a partial positive charge on this carbon rather than this carbon. So this carbon is our most accessible, right? This is the carbon that wants to get attacked or can get attacked. And so the bromine, once again, is happy to do that. So it's going to come in, right, on the back side of that carbon-oxygen bond and break those electrons onto the oxygen. Again, in this SN2-like reaction, right, we have to make, right, this oxygen here a good leaving group, and now, right, it is a leaving group. Right, this OH plus is a good leaving group. We can go from a positively charged species to neutral, right, that makes it a good leaving group. Even though it's still attached to the molecule, this bond is being broken, so it is still performing as a leaving group. And so our final product, again keeping in mind chirality, looks like this, where this side of the molecule hasn't done anything, but the other side that's broken has. So this methyl group was once on a wedge, right? That's where the bromine is coming in from, gets pushed down to be on a dash, and now that bromine here is on a wedge, right? Because again, with SN2 reaction, we're getting inversion of chirality at the attack site. Okay, so hopefully all this makes sense, and if you have any further questions on this, feel free to reach out to me.